Good morning, everyone. I am not exactly sure where I stopped before your midsem. I think I was doing the shear. I think I just started shear. So I hope I'm right. I think we had seen this, no? Have I started this?
Yes, sir.
Okay, fine. So basically, we were just looking at the necessity for shear design and how shear failure looks different from flexural failure. And also we had a look at how shear stress distribution will vary as compared to bending stress distribution. Okay, the relevant formula are also given. So this we had just stopped with. So what we have over here is, see, whenever you have a system of bending and shear, you have a system of normal stresses and shear stresses. Okay. So for example, any point that you take on this beam, any particular patch out of this beam that you take, it will have bending, it will have longitudinal stresses because of bending. It will also have shear stresses because of the shear force. So like that, one element can be taken at any particular point, and this particular point over here will have, if you just take out a certain square or whatever it is, out of that you'll see that it will have a normal stress which is caused because of the bending, and you'll have a pair of shear stresses. Okay, you have the pair of shear stresses because of the shear force. Now, whenever you have a 2D element like this with the normal stresses and shear stresses, you people should remember that you can actually convert that particular system into its principal directions. Okay, you can convert that into its principal directions and principal stresses. Okay. Yes, do you recollect this technique? Of converting normal and shear stresses to a state of principal stresses. Have you studied principal stresses in your mechanics of solids?
Like drawing the Mohr circle.
Mohr circle, okay, yeah. So you have done that. So basically, no, that's basically any Mohr circle which you draw, it is basically going to give you. The use of a Mohr circle is if anybody gives you a set of normal and shear stresses, you would be able to find normal and shear stresses at any other inclination, which includes your principal stresses. Okay, so this is, you might have come across this formula where you can determine your principal stresses sigma 1 and 2, major and minor, as half of, this is actually half of sigma 1 plus sigma 2 into root of sigma 1 sigma 1 plus sigma 2 by 2 the whole square plus tau square. Okay, this is, you would have come across such a formula. Here we have only sigma 1, we do not have, we have only normal stresses on the longitudinal direction, not on the vertical direction. So there is only one sigma. And based on this, you can actually, these are all just principal stress formulas. You can just go back to your mechanics of solids and just recollect that there are formulas like this. So based on that, you can find principal stresses and also you can find your inclination, alpha. Just hold on. Yeah. So that's what is written here. Any element that you choose will have a system of stresses, and you can make them into principal stresses F1 and F2. Okay, and you will see that your cracks will propagate along the direction of the principal tensile stress. Okay, in general, you will find that when you actually find out this value of alpha, whenever you find this value of alpha, you usually find that near the supports the alpha value will be 45, near the midspan the alpha value will be 90. Okay, so this is the reason that near the middle of your beam you have flexural cracks which occur at 90 degrees, and near the supports you will have shear cracks which occur at 45 degrees. Okay, that just so happens because if you take the stresses at this point and you find the inclination, it will be 45. If you take the shear and normal stresses at this particular location and you find the inclination, it will be 90 degrees. Okay, that's how usually the stresses will be present. Now, so what is this ratio? How do you determine whether a beam is going to be susceptible to shear failure or to bending failure? So to know that, you can just look at what the shear stress is and what the bending stress is and what the shear stress is. So you know how to find moment of inertia in terms of breadth and depth, B and D. So if you have sigma, you can write your shear stress, your bending stress as m by, it is actually BD cube by 12, but you can actually rewrite it in terms of what to say, in terms of its. Have you come across? I don't know whether you come across this term called section modulus. I'm not sure whether you come across it. Have you come across section modulus?
Yes, sir, that I by Y.
I by Y. Okay. So basically, if you do I by Y or I by D, it becomes BD square. That's why there's a BD square in the denominator. So M by section modulus, and of course some constant F1. We do not know what that constant is. Similarly for tau, you do shear force by the area of cross section BD times some constant. Okay. So therefore, the ratio of shear and normal and shear stresses, you can just rewrite it in terms of some constant times M by BD, or you can able to see that your ratio of normal to shear stresses basically depends on your ratio of moment to shear and the depth. Okay. So this ratio M by V, you can rewrite it as shear span. So what does that mean? Shear span, what does it mean? So generally, moment is always written as force times some distance. Okay. So any part on this beam that you take, if you take a part section over here, there will be a certain force V or a shear force V. So that V times the distance from the support will be equal to the moment. Okay, so I just use that relation to write M equals V into A. And therefore this ratio M by V, I just write it as A, where A is known as the shear span. So therefore, knowing the shear span and knowing the depth of the beam, you will be able to tell what this ratio will be, sigma by tau. And if sigma by tau is less, that means there's a possibility that there will be shear failure. If sigma by tau is quite large, that means the effect of shear is very less and you'll have more or less flexural failure. So how to find the shear span alone is the question. So shear span is very easy to find. If you have a point load, then shear span is basically the distance from the support to the point load. If you have a uniformly distributed load like this, then the shear span is to be calculated at every section separately. So when we decide for shear, how does the beam resist shear stress? Okay, so this is a broken beam. You can see the angle of this crack. It is inclined. Okay, so you can judge that it is a shear crack. Okay, you can judge that. Two things that you can observe here is here to here there is some change in angle, but you see that more or less it is an inclined crack over here. And in this bottom line, it has become horizontal. This crack has not cut through the beam. Okay, this crack has not gone right through the beam. So out of this, you can actually find, you can actually look at this and say, what are all the methods by which this beam was actually trying to resist the shear. So one of the ways by which it will resist the shear is the concrete itself has some shear strength. Okay. And the shear strength of the concrete has to be exceeded if a shear crack has to occur. So that is the first component, the resistance which is offered by the concrete itself. Okay. The second, another part of resisting shear is something known as aggregate interlock. So basically, in your concrete, you have a lot of aggregates, 12 mm, 20 mm aggregates, whatever they are. So it so happens that sometimes your crack, if it goes and intercepts an aggregate, it is not very easy to cut through an aggregate as it is easy to cut through the matrix of concrete and the CSM matrix. No? That is easy to cut. Aggregate is not easy to cut. Okay. So if at all there is, depending on the aggregate presence of the aggregate, you will have some resistance. And next thing is this is the level of your reinforcement. Okay. And you see that this crack has come over here, come to the reinforcement level, and then the crack has not gone down. It has gone just touching the reinforcement like this. Why has the crack not been able to go through? Why is the crack coming up to the reinforcement and then going like this instead of cutting through? Any idea? No guesses?
Sir, like the steel will be like resisting the bending, sir. So
basically no. Yeah. So at the level of steel, there's steel which will like your aggregate. Steel also has in fact it has it's much more tougher, and therefore making a crack through steel is not that easy. And in addition to that, there's an action called double action, which is also caused by the reinforcement. What is this double action? So basically, if you have a bar and you have basically only shear is going to cause your shear cracking. So if you have a shear across a reinforcement bar which was originally like this, okay, a straight reinforcement bar, and there's shear trying to kind of shear your steel, that is not that easy. So this bridging action by the steel, this is known as double action. Okay. So this external reaction V, or the shear force, if this shear force exceeds the contribution from double action, if it exceeds the aggregate interlock, if it exceeds the concrete resistance, so as when it exceeds all these things, you will have shear failure in the beam. So double action means the tension reinforcement resists the opening up of shear cracks because of the relative movement of both sides, which is not easy to accomplish. So when all these three components of resistance are insufficient, meaning that this plus this plus this, if it's not able to reach the level of your shear force, then you need to provide a separate reinforcement to take shear, which is known as shear reinforcement or stirrups. And one thing which I was perplexed, actually I'm not correcting your Nixon papers, Dr. Deepra will be correcting, but still out of curiosity I just went through one or two papers. For beam design is something few people have actually done shear design with stirrups and all those things. I don't know when I covered it. I don't know whether people even read the question paper and answer, or just look at something somewhere and answer it. Okay. Anyway, I was quite perplexed why people have gone to that. I'm coming to that only now, in fact. Okay, so just a little more look at this double action. So you can see over here three cases. What the double shear force resistance contribution is, that is the y-axis, and the displacement along the perpendicular to the direction of reinforcement, that is double displacement delta. Okay, so I see that if you do not have stirrups or shear reinforcement, when you do not have shear reinforcement, you have a certain bit of double action, and then beyond that, the longitudinal reinforcement or the doubles. Remember, double is not a component. Okay, it's not a separate component like reinforcement or stirrup or anything. Double is just the word used to denote it is just the word used to denote that the longitudinal reinforcement is kind of arresting shear displacement. Okay, don't think double. There are something known as double bars, but that is not this. So once you give a stirrup or shear reinforcement, you see that you have, your double shear force will keep increasing just like what is shown over here. And once it cracks, that the shear reinforcement starts taking the shear force, and we have a further gain in the strength. Okay, so this is another thing, and of course, when you do not have any doubles, I mean, if your double is not cracking at all, then you just keep taking a lot of force. So this is the contribution by double action. You can just see the gain which is obtained. So this graph is showing you something else. It is showing you the contribution to the shear strength of a beam given by the concrete and also by the tension reinforcement. Okay. So when I say contribution by tension reinforcement, it means inclusive of the double action. Okay. So this axis is it says V by BD into root of F dash C. So this is a term which kind of looks at your shear stress with respect to the strength of the concrete. That's why you have FC means in our code book it is FCK. In an ACI code book it is FC. That's it. This one, the below axis, is basically, if you have a look at it, rho W is the ratio of steel reinforcement. Rho is the ratio of steel reinforcement. V and M, they are shear and moment. And of course, you have this, what is this? The grade of concrete. Okay. So you see that until a particular value of shear, until a certain value of shear, you see that your shear force keeps, what do you say, until a certain value of tension reinforcement, rho W. Okay, so when you have a look at this, you are seeing that there is a certain linear increase up to a certain level of reinforcement, certain level of tension reinforcement. And beyond this level of tension reinforcement, there is no more gain in the shear resistance. Okay. So for given grade of concrete beyond a percentage of reinforcement, there is no gain in the shear resistance. That is what is shown by this. Up to say about 0.6 or 0.65, you see there's a gain in the shear resistance, and beyond that there is no gain. Okay. So the reason is beyond this point. Beyond this point, remember that shear causes both. See, okay, what kind of stress causes cracking? Tension or compression? What type of stress causes cracking? Tension or compression?
Tension.
Tension. So when you have a shear state, that means it is a pair of tension and compression. Only then you have shear. Okay. So in the direction where there is tension, this tension reinforcement or the double action will help. In the perpendicular direction, you will have compression caused by the shear. It's called as shear compression. In the direction of shear compression, whatever the tension reinforcement that you give, it is not going to help. Concrete will crush. So that's why you have a limit over here. Beyond this limit, the concrete crushes in shear compression. That's why you have a limit over here saying that beyond this, even if you increase the tension reinforcement, there's not going to be any use. The types of shear failure. So this basically depends on the ratio A by D. We already saw what is A by D. A by D, A is the shear span, D is the depth of the beam. So we saw sigma by 2. It is proportional to your A by D. Okay. So we have this. If my A by D is quite large, if I have quite a large shear span, then according to our code book, it is the limit is 6, I suppose. Okay, according to our code book, the limit is 6. Which A by D is greater than 6, then we say the failure mode is going to be predominantly flexure, and the failure will be either the concrete will crush in flexural compression, or if it's properly under reinforced, it will have failure in tension. Okay, so this is the normal failure which you have been studying in your previous beam design unit. Okay, proper flexural failure. So as long as you have a very large A by D ratio, shear span to depth ratio, then you will have this normal type of beam cracking in flexure. This is known as type. Actually, type and all is actually defined by ACI code. Anyway, whatever you call it, this is 432 and the next will be 1. The type 3 shear failure, it's a case where you have a slightly lesser shear span to depth ratio. Okay. So if it is between 2.5 and 6, okay, then this beam will have some shear diagonal cracks, and at the same time it will also have significant amount of flexural cracks as well. So both, it is still a flexural failure, but shear also starts to influence the failure or influence the strength of the particular beam when the A by D is between 2.5 and 6. So these are all, your question is how do people arrive at this number 6 and 2.5? It is not analytical, it is just observed through experiments. Okay. And later confirmed by some studies, but maybe the chief way of actually coming at these numbers 2.5, 6 and all is several experiments. Okay, there's no other way of that's the way how they fix these limits. Type 2 shear failure is if your A by D is between 1 and 2.5. Okay, so meaning that your shear span is quite short. Okay, and sorry, your shear span is quite short and your depth is quite large. Okay, so because the depth as compared to the shear span is now a little comparable or it is quite big. Who is talking?
Mic on చేసే ఉంది ఇది.
Anybody recognizes whose voice that is? I would be pretty grateful if anybody knows whose voice that is, so that I can actually kick them out of the class and then probably not allow them from next class also. Anyway, so in type 2 shear failure, where you have ratios between 1 and 2.5, these are known as deep beams because the depth has become quite big. And here the failure mode is mainly through shear diagonal cracks, and the presence of flexural cracks are much shorter. And therefore, if you calculate the shear strength of the beam and if you calculate the flexural strength of the beam, you will see that the shear strength of the beam will actually govern your design. And type 1 shear failure is, these are also deep beams and they are really deep beams with A by D less than 1. And flexural cracks are almost insignificant, and you see that your failure, as you see over here on this picture on the right, it is such a short shear span that it will just cut right across the support. The crack will just cut right across the support. So these are the different types of shear failures, and the design which you do here as a part of this course will be it will be mainly confined to the first two cases. Okay, design of deep beams is not in the scope of your current course. Design of deep beams has a lot of other provisions which will be taught only. It will not be taught in a basic R6 course. So you'll be just doing the first two cases. So this is what that shows, the ratio of the A by D ratio, okay, and with respect to the shear force. So that's what you see over here. You see that when your A by D ratio is a moment by shear ratio, if it's quite large, you see that you cannot, your shear force will be quite less and your moment governs, okay. And with a much shorter shear span to depth ratio, your that corresponds to a case where moments are insignificant and shear forces are larger. Okay, so that is what this is showing in general. And of course, it's depending on the grade of the beam and depending on other conditions. This will not be specific values. You have a small band within which these will be relevant. Okay, and the same thing is also shown here. This is shear force and stress at failure variation with the shear span to depth ratio. That is this picture. And this is, I told you, this is how shear stress variation will look. So if you have a rectangular section, top and bottom, your forces will be 0. Shear forces will be 0. Shear stresses will be 0. And at the middle or at the neutral axis, where your flexural stress is 0, at that point you have your maximum shear stress. The average shear stress is generally calculated as V by BD, but because it is 0 here and 0 here, and maximum over here, the shear force at this particular mid height will be 1.5 times the average shear stress. But for our design, generally we do not go with this 1.5 V by BD. We generally just calculate the average shear stress and design it for the average shear stress. We do not design for the maximum. Okay, this is okay because we are going to do only type 4 and type. We are not doing deep beams, so therefore this simplification is allowed when you design the shear beam for shear stress. If you do deep beam design, then you cannot use the average shear stress to design. Okay. So other reason why we just go with the average shear stress is unlike finding flexural stress, finding shear stress is not a very easy process, especially if you have some other shape which is not perfect rectangle. If you have T shape or something else like that, it is not very easy to find this shear stress distribution. Okay, you can find, but not everybody will want to do that. So therefore, just for our convenience, code says go ahead with the average shear stress. So sometimes we can also have cases where we have tapered beams. An example of a tapered beam is your sunshade. Okay, sunshade is not a beam; it's a slab, but that shape you can imagine. A sunshade will be broad at the wall, and towards the end it will be coming narrow and narrower. So that's a tapered section. So if you have a tapered section, how to get the shear stresses? So this is just something which shows that not that important. So basically, this is the line of our reinforcement. This dotted light blue line. Here is our compressive stress from the flexure, and this is our tensile stress from the flexural stress taken by the reinforcement. Vx is my shear. So this all will be just resolved, and then you can just get by just doing taking this lever arm. So Cx Tx with that particular lever arm gives you your moment. Cx equals Tx equals mx by this depth z, not section modulus. This is depth z. And if it's quite a deep beam, then instead of saying z, you can in fact just approximately replace it by d. And then of course, then this is all just you're just doing equilibrium along the vertical direction. Okay, so you just look at these forces, right equilibrium, you get Vx. The net shear force is Vx minus Tx tan beta, and instead of Tx you substitute Tmx by d and you get all this. Okay, and if beta is sloping upward, then you use plus sign. If beta slopes downward, you use a minus sign. Okay, and this is the net shear force. If you want the shear stress, you just divide the thing by area of cross section BD. Why I showed this is for normal rectangular section, you know how to find average shear stress, which is V by BD. If it is tapering, how do you find the shear stress? So this is how you find the shear stress if it is tapering. Okay. So just for that purpose, this was shown, nothing else. And now where do you calculate the shear stress? So moment everybody knows what to do. When I'm giving you if I give you a simply supported beam with UDL, which location do you calculate the moment and design?
It's fine.
At the? Not audible, not audible.
Center side, mid span.
At the center. Okay, why do you take it there?
Because at that point the moment will be
Maximum.
It's maximum there. Okay. Now where will shear force be maximum? In a simply support beam with UDL?
Support.
At the support. So when you just look at it, you would imagine that okay, to design a beam for shear, I should calculate the shear force at the support and design that beam for shear. But code says no, don't take it exactly at the support. It says take it at a distance d from the support. So if you have a beam with a certain shear force diagram, don't take the shear force value at exactly the support. Go to a distance d away from the support, find the shear force over there, and then design for it. Of course, the shear force that you calculate over here might be lower than the shear force which you calculate over here. So if somebody does not want to go draw the shear force and find the shear force diagram and then find out d from the support what is the shear, if somebody does not want to do that, then just find it at the support and design it, because anyway it's going to be conservative. But I still have to tell you what the code says, so I'm saying it. The code says the critical section for shear is not actually at the face of the support, but it is at d from the face of the support. Now why does it say so? It's because near the support, if you have a look at this, there's P over here, reaction over here. So there is a flow of forces from this place to this place, and therefore there is a bit of compression happening between the support and this place. Okay, there's a bit of compression. This compression tends to actually increase the resistance of that particular portion to shear. Okay, so the reasons for this are not exactly tellable, but these are also observations which people have made, that between the support and d away from the support, there is quite a lot of compression happening within that zone, compression within this region like this. Okay, so there the shear is not critical. So therefore they say if you go d distance away from the support, if you go, then here that effect is not that much present. So therefore here the shear will be critical. And in fact, when people do experimental tests, when they see that so we saw three components for shear resistance. One is resistance of the concrete itself, then there is aggregate interlock, then there is double action. Okay, so combining all these three, that IS 456 gives you a table where, depending on the percentage of steel and depending on the grade of concrete, you can find out how much is the resistance to shear for a given concrete beam which does not have shear reinforcement. Okay, a beam which does not have stirrups. Can the beam take any bit of shear? Okay, so to answer that question, you can just in IS 456 this equations will not be there. Rather, you will have a table which gives the results of this equation. So you will have, I think the next slide the table will come. So basically the shear force or the shear stress, shear strength of a given concrete with a certain percentage of steel. It depends on grade of concrete, it depends on the percentage of steel, where this parameter beta is something which depends on your percentage of steel and FCK or 1, whichever is greater. Okay, so based on this, you just calculate it, you will get a certain value of tau c. And how do you, so in case you know how much is the shear which is coming in your beam. For example, VU is the shear which you need to design for. Okay, VU is the shear which you need to design for. VUC is the shear resistance of the particular concrete beam. Okay, so if this VU minus VUC, if VU is greater than VUC, the beam is fine. You need not give any shear reinforcement. if VU, if VU is lesser than VUC, you need not give any shear reinforcement. Okay, because VUC is greater or the strength of the beam is greater than the and then the shear which is present. However, if VU is greater than VUC, meaning that the actual shear which is present is greater than the shear resistance of the beam, then you cannot leave the beam as such. You need to give it separate reinforcement for shear, and that shear reinforcement should be able to resist a shear equal to this value, equal to the difference between the applied shear and the shear strength of the beam. So this shear strength of the beam is easy to calculate. If you know tau c, you can just multiply it by the area, you get what is VUC. Okay, and of course this what to say, even if you give shear reinforcement, you cannot I'm not saying not give shear reinforcement. This tau c, for every grade of concrete there is a certain limit set on it. Okay, this limit is approximately equal to 0.62 root of FCK into a BD. So this tau c max is the upper limit placed on tau c. Okay, meaning that for any given grade of concrete and any given percentage of steel, the strength of the beam has an upper limitation. The reason for the upper limitation is because the same reason which I told before, it is for shear compression. Okay, if shear compression happens, then steel reinforcement is not going to help you. So the shear reinforcement, they are called as stirrups. And just like how you saw in designing a beam, you had a formula to calculate the percentage of steel. Okay, to calculate the area of steel. So we had, depending on the moment, depending on the neutral axis distance, okay, grade of concrete, grade of steel, depending on all those things, you had a formula. Okay, that P equals 50 FCK by FI root of 1 minus 4.59. The big formula you had, based on which you calculated the percentage of steel to be given for flexure. And that formula was based on the moment which is actually present in the beam, or the balanced moment, whatever you do. Similarly, for stirrups also you have a formula which, depending on the shear force which is present, you can use the formula to obtain what is the area of shear reinforcement that you need. Okay, so basically it is given as 0.87 F by ASV D by S subscript V into sin alpha plus cos alpha. Okay, so what are the meaning of these terms? VUS is the difference between the applied shear and the shear resistance of the beam. So that is the shear which has to be resisted by the shear reinforcement. So that is this 0.87 Fy. All of you know what is 0.87 Fy. ASV is the area of a single stirrup. Okay, so before you are able to know what area of a single stirrup means, you will need to be shown a picture. I will show that in the next slide. D is the depth of the beam. SV is the spacing of the stirrups. Okay, so what is the spacing between one stirrup to the other stirrup? That is SV. This alpha is in case your stirrups are not vertical, and if your stirrups are inclined, that inclination of the stirrups with respect to the longitudinal reinforcement, that is alpha. In most cases, we have vertical stirrups. Okay, in most cases we have vertical stirrups, meaning alpha is 90 degrees. So therefore this is 0 and this becomes 1, and we have 0.87 Fy ASVD by spacing SV. Okay, so this is the most common used formula for finding what the shear reinforcement is. Here we have VUS, we will know. It is because we know the applied shear, we will know the shear strength of the beam. So therefore we will know what is VUS. Fy know because we know what is the grade of steel. D also will know because we already designed the beam for flexure, so we have given a certain depth. How many unknowns are there in this equation? Given that VUS, Fy and D are known, how many things do you not know? You do not know 2 things. So because of that, since there are 2 things which are not known, there's no other way. You just have to assume one thing and find the other. The most common thing to do is assume area of a single stirrup and then decide how much they should be spaced. That is the most common way of doing it. So I showed you a formula here. Okay, so this whole thing is actually tabulated in IS 456 in this way. Okay, so depending on the grade of concrete and the percentage of steel, you have the values of tau c or the shear strength of the concrete. Look at the values. It's all point something. Okay, your grade of concrete, if it's M35, okay, it's M35. Even if you take 0.36 FCK, okay, 0.36 of 35 is almost, it's greater than, it's about 12 or 13, okay, 12 or 13 Newton per millimeter square. But tau c is only, even with 3 as the reinforcement, okay, still your tau c value is only 0.99. Okay, you can see how less this is. Okay, it's a really small value. So in many cases, you will see that just by doing tau c into BD, you may not be able to get what is the required shear strength for the beam, and therefore you will go ahead with providing some shear reinforcement. And even if you give the shear reinforcement, okay, still the maximum tau c, okay, that you can actually reach is only 3.1, 3.5 or 3.7. What is this tau c? This tau c is nothing but you have your you have your applied shear, okay. That applied shear should not exceed any of these values, okay. The applied shear stress, the applied shear divided by BD, will get a certain value of stress. That particular stress should not exceed 3.1 if M25, it should not exceed 3.5 if 30 and 3.7 if 35. And this is even if you give shear reinforcement, still you cannot just because you have you're having M30 concrete and you're getting applied shear stresses, say 5 or 6 Newton per millimeter square. Even if you give shear reinforcement, you're not allowed to do that. You should still restrict it between these values. Okay. So this I already told you, if your shear span by depth ratio is greater than, it's lesser than 2 or 2.5, it becomes a deep beam. A deep beam complying with the requirements of 29.2 and 29.3 shall be deemed to satisfy the provisions for shear. Deep beam we are not going to do. Okay, so don't worry about it. And these are just some extra provisions saying that if you have an axial member, for example, a column, if you're having a column which is also having shear, then it says that you can just increase these values by this factor. Okay, so we will not be doing that, but just need to know that it's good to know that these kind of provisions are there to help you if you need them. Beams are varying depth. This also I showed you that if you have a varying depth with a certain taper, then depending on the taper you can find out what your, this is how you calculate your shear stress for that particular case. This also I showed you, critical section should be at D from the support. So this is how a shear reinforcement will look. Okay, it will look, if it is a rectangular beam, it looks like a rectangular hoop. Okay, and it will be bent like this, brought over and again bent for a certain distance. So this distance is important. So you had this, I think in your SP34, that code book which I showed for for helping you draw the one-way slab detailing. Then if you go to shear, I think you will see how much this length should be, how it should be tied, and all those details will be given there. You can actually have a look at it. And these things are known as stirrups. So basically what you'll do is, this is known as a two-leg stirrup. Okay. So why it is called a two-leg stirrup? Because you look at it in the direction of the shear. My shear is vertical. So therefore in the vertical direction I have one leg over here, another leg over here. So this is two-leg stirrup. So you can either hook it like this, but this is not recommended. The most recommended way of hooking a stirrup is the second one. Okay, having a hook bend, bringing it down, bringing it over, and then coming and bending it again. Okay, this is the most recommended way of actually doing your stirrups. So this is a two-legged stirrup. So the way of calculating ASV in the previous formula, ASV are the area of shear reinforcement of a single shear reinforcement is how many legs does it have times what is the diameter of the stirrup. Okay, so if it's a two-leg stirrup of say 8 mm diameter bar. Okay, so one 8 mm diameter bar cross-sectional area is 50. This has two legs. So the ASV for a two-legged 8 mm stirrup is 50 into 2, 100 mm square. So in the previous formula you will substitute 100 over here and find out SV. Like that, depending on how big or how wide your beam is, how deep your beam is, and depending on how many layers of reinforcement that you have, you may need more legs for the stirrups, because every layer of reinforcement should be surrounded or should be hooked with a stirrup. So if you have 3 layers, then you can give one stirrup which encloses this, then you can give a stirrup which just encloses this alone, or you can give a stirrup which encloses this and this, and you can give a stirrup which encloses this and this. The options are yours. You can give any option as long as you do not violate any caudal provisions. So this is 4-leg stirrup because 1, 2, 3, 4, and this is a 6-leg stirrup because 1, 2, 3, 4, 5, and 6. Okay. So depending on the number of legs, you just multiply it with the area of a single leg. That will give you the area of the thing. So this is how you tie the reinforcement or welding with the main hanger bars. Hanger bar means it is in case you have a singly reinforced beam, which also does not have any negative moment. So you're not giving anything on the top. Say you have a situation like that. There also, just because you need to give shear reinforcement, you have to give a bar at the top, a very small bar at the top, 8 mm or 10 mm whatever, so that you can hang your stirrups. So stirrups can be vertical like this, okay, because this is the most easy way to actually tie your stirrups with the longitudinal reinforcement. So this is the most preferred and most easy thing to do. But the most effective thing to do is to make it at 45 degrees. So why do I make my stirrups at 45 degrees? Why is it effective? What else is 45 degrees? Yeah.
Yeah, the shear crack will be like approximately.
Shear crack is also at 45 degrees. So if it proceeds from it, it will go and directly intercept it. So 45 degrees is the easiest, most effective thing to do, but tying and all those things are problematic. So not many people prefer to do this. So stirrups can have many legs viewed in the direction of the shear, which is usually vertical and depending on the width of the beam. Okay, so with this I'll stop design of stirrups. So today's Friday now. Okay, so then next class we will do a problem on design of shear, and then we'll go to torsion design of RCC beams. Prabha ma'am's class is over or still going on?